Hello, hello. Let's see. Go to share screen and go over to the complexity lecture. Share. Okay. So, oh God, I just got something in my eye. It's sunscreen. Either that or some sort of like moisturizing type shampoo type thing. I'm gonna go over here because the lighting is better. Haha. Yeah, that seems good. All right. So, oh wait. Complexity theory. So this appears like this will be the last topic on your exam next Thursday. We'll cover hopefully a third of it today, a third of it on Monday, and a third of it on Wednesday. And it feeds quite well from the previous lecture talking about feedback loops and positive and negative feedback loops and collective outcomes of whole systems like social groups, brains, ecosystems, anything where there are many kinds of interacting subunits that influence each other's behavior, those synergistic outcomes or emergent outcomes. Complexity theory, by the sound of it, sounds like it would be complex. And mathematically, contextualizing these concepts actually is quite complex, but the concepts themselves are actually pretty simple. So we're going to talk about complexity theory from a qualitative standpoint that covers all of the necessary topics so that you'll be literate and conversant in this field, which innervates many kinds of science. And hopefully you'll realize that it's not, although it's kind of spooky in the way it sounds, in reality, it's kind of, it's pretty straightforward, I find. Anyway, so your exam next week, guess what? I'm going to give you a little more time than last time. I will probably give the standard student something like an hour and 15 minutes. Anyone who needs special accommodations will have proportionally more based on that increase. I will try to have the exam up on Thursday morning by 11 a.m. You'll have this enforced time limit. It will not be password protected like it was last time. Whoops-a-daisy. And then I should have, I'll keep it open until Sunday for folks who have special accommodations, and everybody else, you gotta have it done by Thursday night. I'm so sorry. Again, it's multiple choice. Oh, your exam questions. If you intend to give me prospective exam questions that you'd like for me to evaluate for possible inclusion on this exam, please have those to me by Monday night. So by Tuesday morning, I'm going to be finalizing that exam and uploading it onto Avenue, which takes a surprisingly large amount of time because each and every option, each and every option, I have to copy and paste into a little cell. On the one hand, it's very straightforward, and so it would be almost impossible to mess up, although I managed to mess it up last time in at least one instance. However, what the downside is that you can't just upload all of the questions in an automated format. So they can't just read an Excel document or read a Word document and automatically format it appropriately. So it involves lots of copy and pasting. Poor me, it's going to take me at least an hour and a half or 2 hours of copying and pasting to create that exam. And there are a lot of opportunities for mistakes when you're copying and pasting over and over and over and over and over and over, let me tell you. Anyway, complexity theory. So complexity theory basically says brains, solar systems, social groups, piles of dirt, all of these systems involve interactions between subunits that are sometimes like each other, and sometimes there are categories of subunits, male and female and aggressive and docile or whatever, or they could just be more or less equivalent subunits that just look alike and behave in a similar way, follow the same rules. But in order to understand the outcome of this aggregate, a brain, a social group, a society, planet Earth, an ecosystem, you have to understand how those individual subunits interact with each other. So the collective outcome is very rarely just summing up or averaging the behavior of what individual subunits would do in isolation. In social groups, what individual social animals would do in isolation, because they attend to each other's behavior, and the behavior of one member of the group will change the behavior of others. So to understand the emergent outcome, you have to understand the nature of these interactions between individuals and how those change based on external environmental parameters. So how do the interactions or the rules that individual social group members follow, how do those change based on whether it's dark outside or light, cold or warm, whether it's mating season or migratory season, et cetera, et cetera. And the rules and the amount that individuals weigh those rules will change based on environmental parameters that surround the social group, right? And no shock, feedback loops. The idea that one kind of behavior or response in a social group member might instigate a similar behavior in another social group member changes the collective outcome. You bet your boots. And so likewise, if one individual engaging in a behavior decreases the other probability that other members of the group engage in that behavior, that also will change the anticipated collective outcome relative to just a null expectation of what individuals do on their own. Complexity theory says that complex systems that have lots of parts and lots of interactions are highly unpredictable. They're difficult to predict the outcome of the system based on inputs. Yet, what's key is that they're constrained. The systems of these things, the systems are not random. They might appear difficult to infer or be able to predict, but the reality is that they're following a limited number of rules that could be described mathematically by things like differential equations. And with a relatively small number of rules, you can create or reproduce collective dynamics of social groups, brains, ecosystems, at least qualitatively, in silico, i.e. in a computer. So, some terms here. A parameter is an environmental feature surrounding your collective unit. The parameters of the human brain might be something like the external environment or the endocrine profile of the host, like your brain's a parasite, but like the host is the person or individual containing the brain. Or it might be something like the external environment, visual stimuli or acoustic stimuli or whatever, right? It's an external feature that is surrounding the brain that will change the forces acting on the brain. Parameters are external to whatever you're focusing on. Parameters for a social group might be something like whether or not it's raining outside, light or dark, whether it's arid season or wet season, et cetera, whether or not there's a bunch of traffic noise nearby or not. So, but a parameter for something like an ecosystem might be something like global precipitation levels or evaporation rates or things, external to an ecosystem. So what is external and what is internal, what is a parameter and what is a state, which we'll get to in just a second, will change based on what your focal system is. As a social group, anything beyond the social group is a parameter surrounding it, an environmental feature that will change the rules that the social group is following or how they weight them, which will in turn change the collective output of the group and how it behaves. States are internal to your focal unit. So states are a measurable characteristic or output of the system that you're focusing on that typically are qualitatively distinct. Are you migrating or are you staying here? Are you huddling together or are you diffuse? Are you going out to forage today or are you staying in? These are qualitatively distinguishable outputs that you can categorize. And if you graph them, might be clustered out in parameter space so that they do appear like qualitative states. A cloud of values over here, like number of individuals that go out to forage in an active colony, and then a cloud of points around here. Relatively few or no individuals going out to forage. So those might be two qualitative states and not have a slur of points between them. So, right, it's not a complete gradient. Now, nothing is ever completely qualitatively distinct. That's one of the things like, oh, this term and that term, there's gray areas. Well, guess what? In life, there's always gray areas. And of course, mathematically, there are gray areas too, when you plot things from real data. And so, no shocker, although there is always a slurry of points in between, if there's a general two pairs of clouds or two regions that a graph would depict are distinct from each other, that a social group can occupy or a brain can occupy or whatever, and whatever you're measuring, then you could call those qualitative states. So a state is something you measure about your complex system, usually that are qualitatively distinct that you're trying to look at with the system flipping between. And a parameter are external forces that change the probability of that social group occupying one of those states or another, and the kind of rules they're following that determines whether or not there's a state at all. Nonlinearity. I'm very impressed with my pink coloration scheme here, so haha. Nonlinearity is one of the classic features about complex systems and complexity theory. Nonlinearity is exactly what it sounds like. Guess what? The relationship between some input, some parameter, and some state is not a straight line. So maybe it's sigmoidal, where there's an accelerating function and then a decelerating function and a stable component, right? Or maybe it's concave down, it's parabolic, or concave up, it's parabolic. Or, you know, whatever, it could be an elephant, right? It's just a swirly whirl. It could be a sine function in polar space, right? So whatever, not a straight line. Most things in life, if we just had enough data, wouldn't be a straight line, right? There'd be subtle shifts in the relationships that we see between inputs and outputs of any system, be that an organism, a brain, a whole social group, an ecosystem, whatever. The biosphere, i.e. planet Earth. Okay, so let's look at population growth rates of any kind of animal population, social or not. When the population has very, very low numbers of individuals, they tend to remain in that state because it's difficult for individuals even to find each other to copulate and reproduce, assuming that they're sexual organisms, not asexual organisms. Yes, there's an exquisite amount of diversity of how animals reproduce, and I fully abdicate that point, but we're going to pretend that we're just some boring population of like sexually reproducing animals, nothing interesting, something very Puritan. Anyway, so imagine that we are just two discrete sexes. Again, I'm aware of all the criticism of this as well, and you don't have to make that point to me, but let's pretend for a minute that we can easily categorize males and females in some generic population, at least in a computer that we simulate. If we make them at a low enough density, they can't find each other to mate. And so the population will tend to stay at a low population size for a variety of things like resource levels or time or whatever. Now, when we reach a certain level of population size, individuals no longer are, population is no longer limited by the ability of individuals to find each other to copulate. And guess what will happen? If the population has a large amount of resources, it will increase, not just slowly, but exponentially. Initially slowly, but then it accelerates through time. So we get this positive acceleration here, and then that's actually a linear phase. I don't know why I continued to say it's exponential growth, but like a linear portion here, and then a nonlinear portion here, a linear portion here, and then a transition to a decelerating nonlinear form here. So the rules that are happening here, that are determining whether or not that population stays at a low population size, are basically just a lack of ability of subunits of that population to interact, males and females, right? However, once that key density is reached, they can now mate with each other at a high enough rate, and that will increase their density. And because there are more individuals, they're going to find each other even more easily, and they're going to find more mates, right? And then assuming that the reproductive output of the population is determined by the number of females, which is more or less usually true because they produce eggs, and eggs normally determine how fast a population can grow, if they can be fertilized. So that population will grow at a faster and faster rate until a new process begins to force that population to decelerate. During this acceleration phase, guess what's happening? A positive feedback loop, just like we talked about last time. Individuals reproducing at the next time step will cause more individuals in the population to be able to reproduce, which in turn create even more individuals that can reproduce. And this is a positive feedback loop that causes the exponential growth rate of things like a human population or coronavirus incidents. Anyway, what a neat topic. Thank God coronavirus happened because it's really helped my teaching. Anyway, all right, so but then a new process occurs over here, right? There's a transition phase. We're now, because this population has a resource that it's consuming, at some point it will reach a critical level of density where now a new process is causing a negative feedback loop. This decelerating phase here means that there's something mathematically, effectively, if you were drawing little vectors in a field, that's pushing the population away from further growth. And what is that? Normally it's resource limitation. At this key threshold here, now resources become limited and begin to decrease the amount of reproduction that each individual can engage in because they just can't yolk that many eggs. They can't get that many offspring to survive, et cetera, et cetera. And so you have a transition phase where you have a negative feedback loop that begins to prevent this population from exceeding this boundary, which is called a carrying capacity, i.e. the number or concentration or density of individuals of a given species that can occur in that area. So a positive feedback loop caused that population to accelerate, and then a new feedback, a negative feedback, forces that population to not move beyond that boundary layer. But that population doesn't suddenly drop off, right? Unless it way overshoots its carrying capacity, and then there's a massive die-off. If it approaches it slowly, and that will tend to happen because of a negative feedback loop, the strength of that negative feedback loop gets larger as individuals approach this boundary layer or exceed it, and so the population will tend to approach that slowly and then wave around it. Now there are two feedback loops that keep that population at that side. A positive feedback loop that will be triggered if the population gets to a low enough size that it doesn't become so resource limited any longer. And a negative feedback loop that prevents it from getting any further beyond this carrying capacity, at least very far, right? So this stable state, this carrying capacity, which is the number of individuals in that site of whatever species this is, elk, mice, I don't know why I picked mammals, corvid birds, will tend to be pinned there by these two processes. Things that tend to remain at a given state and fluctuate very little, or move towards that space, towards that carrying capacity when they're displaced, are stable states. Things that more or less, if we pull that population away from that spot, we make it artificially large or artificially small, will tend to be drawn to it. And those forces will be positive and negative feedback loops, right? Cool. Most models of economics, which we spend a lot of time and money on, like by definition, ecology, which we need to pay attention to because we've only got one biosphere, and the behavior of society, which influences all of this because we're humans and we have kind of a hegemony on planet Earth ecologically, our own behavior. Most of our models of these systems, economics, which is complex, ecology of ecosystems or social groups, endlessly complex, behavior of individual humans, incredibly complex. All of these models that we create are mostly linear, which means they do not account for positive and negative feedback loops. They do not account for nonlinearity, mostly because we don't have a high enough quality of data. So, and for simplicity's sake, it just requires more math to make them nonlinear. So people just say, coarse approximation, we think this relationship should be like this. But the reality is most systems have nonlinear feedback loops, and that's what creates stable states and what causes them to break down. If something about the external environment caused that positive and negative feedback loop to break, then the stable state of the system would shift, right? The number of individuals of a species that could persist through time could change. How could that be? Well, let's pretend that these are some sort of food-limited ant, we'll say, right? So it's the number of ant colonies that can subsist in an area, and they live in a relatively arid area where they are water limited. And then we'll say you're in a suburb or just outside of a suburb of Phoenix, and not Phoenix, Arizona. It's a hot desert city that shouldn't exist with millions of people in the middle of Arizona. It's famous right now because they can't get their voting counts in order. Anyway, so but then there could be a development, right? Somebody creates a neighborhood and irrigates this place that was formerly incredibly dry. Well, now the number of ant colonies that can subsist in the area could go up dramatically, right? The water is what's preventing these colonies or their seeding plants that they rely on from reaching higher levels and more colonies of these ants for flourishing. Well, that could all go away if we suddenly irrigate it, right? So the positive feedback loops that maintain these stable states can break down based on external parameters, which is what we'll get to later on. Jensen's inequality. This is another feature of nonlinear systems that needs to be kept in mind, and that is the impacts of increasing the variance, i.e., basically creating noise in a parameter, will change. So, like if I was allowing something along this x-axis to jiggle back and forth, and that means sometimes. And let's say it's jiggling back and forth on this line, this first white line between the lagged phase and the exponential phase, and we're measuring the population size. If sometimes, just by some chance, the population got shunted down, every so often there are die-offs, and they seem to be totally stochastic, random. If it caused them to go down, to this point here, then we would see that the population size would be quite low, and they would no longer be able to find each other at a high enough frequency to be able to instigate that positive feedback loop. But if they had just by random chance, a surge in survival in 1 year, or someone didn't mow the lawn and kill off a bunch of them, and you suddenly pop the population up here, a symmetrical distance along the x-axis, here versus here, well, now suddenly the next generation could have an enormous impact on population size. Look from this point here. If we went over halfway and went down, that's a relatively small difference in population size. But then increasing variance in the opposing direction would cause an enormous increase in population size. And that's because this is an accelerating function. If it's an accelerating function, I'm gonna make it reverse on your screen because it's a mirror here. If there's an accelerating function and by random chance, there's a decrease of half of whatever this variable is on the x-axis, it's going to have a relatively small impact on your response variable. But if you increase it by the equivalent amount on that x-axis, the outcome in terms of population size for this figure will be much greater than the opposing direction because it's accelerating. Let's imagine that it's the exact opposite up here now. So now you're in this transition phase, right? Where you can have a stochastic chance where you cause an increase in whatever this variable is on the x-axis or decrease. Well, a decrease now causes a precipitous drop-off, and an increase causes almost no, an ephemeral increase in population size could cause no prolonged increase in population size at all, right? Because increasing variance on the x-axis in a decelerating function causes steep drop-offs on one side and very small returns on the other. Showing this graphically, XA, 2A, and increasing by some amount, and a decreasing of some amount in an accelerating function will cause a very large increase and a relatively small decrease. So there is a relatively small impact right here. So if this is the anticipated outcome, and decreasing it here, decreasing it by some amount to 1A, that causes that big of a drop off. If it's in the accelerating component of this function, then it will cause that large of an increase in whatever this response variable is. If you're in the decelerating component of this function, then the drop-off can suddenly become much greater, right? So now the anticipated drop-off from decreasing x by some value will be much greater than the anticipated increase if we increase whatever this is on the x-axis. So this is all kind of opaque right now. Adding variance either can cause disproportionately large increases in an accelerating component of the function, and relatively small decreases in the accelerating component of a function. And then if it's leveling off, the potential drop-offs are large, and the potential increases for increasing whatever x is quite small. A linear function, if there's just a straight line, the effects of increasing the variance on the x-axis is always going to be completely symmetrical on the y-axis if it's a straight line. But if it's an accelerating function, increasing that variance is always going to cause a disproportionately large increase in the response through time. And in a decelerating function, the opposite would happen. Anyway, the important features here are, one, you know that increasing variance has different impacts based on whether you're an accelerating function or a decelerating function. If you're an accelerating function, then increasing that variance is going to tend to cause a disproportionately large increase in the output on the y-axis if it happens over and over and over again. And the opposite will happen with a decelerating function, a concave down component of these figures, which means that if we add that increased variance over and over and over, then we're going to get, the times that we get the drop-offs, it's going to be huge. And the times that we get the benefits, it's going to be teeny tiny, which means over time, adding variance on that x-axis is going to cause a disproportionately large depletion in whatever the y variable is. All right, let's imagine a real-life example. We're going to talk about cats. I bring up cats a lot, but here we are. We have two ginger cats on the right-hand side here, and we're going to talk about caloric intake. Well, if you're a very, very skinny cat, and you have, emaciatedly skinny, teeny, tiny, gaunt cat, well, feeding that cat a little bit more, although it might enjoy it, it might light up its brain with serotonin or dopamine. Maybe both. Anyway, it ignites the pleasure systems in this cat's brain. That's great, but the anticipated increase in this cat's fitness might be very nearly zero. if it's very skinny. Why? Because although it might live for a little while longer, it's probably not going to have enough calories, we're proposing these are female cats for a second, to be able to bear offspring. So although you've made the cat somewhat happier and it has, you know, a wonderful moment, it probably can't reproduce. It's effectively a fossil. Now, there's probably some intermediate cat sizes where the cat is kind of skinny, but not so skinny that if you fed it a little more, that it could not reproduce. So at some point, you might have a cat that's skinny, that if you don't feed it, it won't reproduce. But if you feed it a little bit more, it has a chance, some chance of reproduction, right? And so you have a relationship here between food intake and anticipated increase in fitness, reproductive output. Skinny, skinny, skinny cat, you're basically at this flat component of that population growth curve, where like even if you feed it a little bit some days and not others, it's just not gonna have any reproductive output because it just doesn't have enough food to reproduce, enough to just sort of like death rattle onward. Okay, food to death rattle onward. Okay, now a little bit of a fatter cat. Okay, if that cat now is at the point where if you just got a little bit of food on some days or some years, it could reproduce those years. You would be in an accelerating component of that function. The amount of food it's eating right now, not going to reproduce. But if you increase variance, some years, some months it gets a little more food. Some years, some months it gets a little bit less food. Well, then that cat is now at an accelerating function, right? Where a decrease, since it's already incapable of reproduction, means it's not going to impact its fitness at all because it's not going to be able to reproduce. But on those lucky months, those lucky years that it gets enough food to reproduce, then it has some small amount of fitness. And that means that for this skinny, but not super, super skinny cat, it can reproduce sometimes. So adding variance at an accelerating portion of that food fitness relationship can change that skinny, but not so skinny cat's life in terms of reproductive output. And then for lots of cats living on the streets, more food means it can ovulate more regularly, bear more offspring, lactate more effectively, and rear more offspring, right? So you're at that sort of like accelerating exponential or flat linear component of that curve, moving upward. Now, but there is no such thing as a resource add fitness output increase without bounds, right? There will be some decelerating component at which time the cat cannot reproduce anymore. It is no longer food limited, right? The cat is so overwhelmed with resources that it's no longer resource limiting. It's no longer resources that's limiting its ability to produce more offspring, right? It's something physiological. It's something about its endocrine cycle. It's only able to go into estrus every so often, right? And think of about a very, very fat cat. So now we're like way up on this decelerating component of the figure where adding more food to that cat's life, it's not going to increase its reproductive output at all. But if we take it back a little bit to where the function is decelerating, but it's not way out on that asymptotic component yet. So a very, very fat cat would be way out on this asymptotic function. Like even if you fed it a little bit less or a little bit more, still going to have the exact same reproductive output. Assuming there's not like some sort of adverse effect of being an obese cat on reproductive output, which there may well be, but let's pretend that that's not true right now. But if you're at a cat that's pretty fat, almost optimally fat, it's on the cusp, and you begin to vary its food intake on the x-axis, there's a chance that if you give it more food, you're not going to have any increase in its reproductive output. It's at the precipice where it's basically getting the maximum amount of food that could still increase its reproductive output. But if you suddenly decreased its food intake, it actually would, since it's a decelerating function, it actually would have a decrease in its expected, anticipated reproductive output, right? So there's a threshold very close to optimal fatness for reproductive output that you could lose fitness by varying its food intake if it goes down, but increasing it would have no impact at all. Why? Because you're at a decelerating function. Anyway, census inequality and caloric cat fitness. But you know, human society, right? Money doesn't buy happiness. That's actually not true. Actually, money does positively associate with things like happiness. So this is at the national, global level where we're looking at countries that have some amount of per capita GDP. Again, we know that that's like kind of a weird statistic because it's not equally distributed across all of the inhabitants. And right now we're talking about whole countries and proportions of individuals that feel highly satisfied with their lives and not the emotional states of individuals, but these are aggregated statistics at the levels of whole nations. The number of people who feel satisfied with their life, the proportion of people who feel satisfied with their life is lower when the per capita GDP is really, really low. And when you have really, really productive societies, well, guess what? They tend to be happier, right? They tend to be happier. A higher percentage of them tend to feel satisfied about their lives. Yes, there are still people who don't like anything and see problems everywhere. And yes, there are people who are gloriously happy, even under the most horrible of conditions, because there's individual variation in happiness, that a lot of it appears to be heritable. But at least here, there is a positive relationship between per capita GDP and the level of population, the proportion of the population that feels satisfied with their lives. But it is highly nonlinear, right? Presumably, there's a very, very low level of GDP where, like, even if you increase the GDP slightly, nobody would really be that much happier, right? It's just so bad. Everyone's unhappy, and increasing it slightly is not going to make anyone else feel more satisfied. This is a decelerating function, though, which means up at this higher level here, like, proportional increases in GDP do not cause proportional increases in happiness any longer. And the sad thing about this is that this whole relationship appears to be decelerating, which means adding noise, adding gambling across some years you would have the higher levels of GDP, and some years you would have lower levels of GDP, versus strategies that just keep the GDP where it is. Do not gamble, or at least have a low variance strategy. That seems to be most optimal under these conditions for the perception of happiness in your population. Because if you start gambling on this x-axis here, having some years where you have high GDP, some years that you have low GDP, well, you're at a decelerating function, which means you stand much more to lose than by varying GDP than you do to gain by gaining the symmetrical same amount of GDP. So adding 5,000 on the per capita GDP has a smaller impact on percent of the population that's satisfied than decreasing it 5%, right? Decreasing a GDP by 5% causes a proportionally larger drop-off. And when it's a steep area like this, good gracious, dropping it by 5,000 causes almost, a 15% decrease in perceived happiness. Increasing it by 5,000 causes less than a 10% increase in happiness. So don't gamble if you're in a decelerating function. Do the safe, assured thing under those conditions. If it's an accelerating function, gamble. Why? Because the proportional gain in causing variance on that x-axis is going to result in, on average, if you do this over and over and over, disproportionately large increases. Anyway, there you go. Feedback. I'm going to go over this portion quickly because I actually want to finish complexity before the next exam. Positive feedback loop catalyzes behavior of like behavior in the social group. Negative feedback loop diminishes like behavior. Positive feedback loops tend to cause accelerating functions. Negative feedback loops tend to cause a decelerating function, so it prevents it from continuing to move without bound. Think of social mobbing. Social mobbing is a fabulous way of thinking about positive feedback loops. If you start saying negative things about individuals on social media accounts, that will tend to catalyze other individuals to share their negative views, and that will catalyze and give permission to more individuals to share their negative views. And this can cause positive feedback loops where individuals feel overwhelmed by negative attention from their peers and beyond. Has catastrophically negative impacts on people's psychological and social state. Go easy. All right, feedback loops. So as I said before, stable states are pinned usually by feedback loops. Some feedback loops prevent individuals from, prevent the population from moving further in one direction, or the system from going further in one direction, and prevent it from moving the opposing direction by other feedback loops. In the case of the population size scenario, it's exponential growth from a stable intrinsic growth rate and resource limitation that pins populations at their carrying capacity. I mentioned mobbing already, but like popular opinions tend to catalyze popular opinions in politics, and negative opinions tend to catalyze negative opinions. Once individuals around them feel like the majority of individuals nearby share an opinion, they're much more likely to voice that same opinion. Why? Because it gives you a sense of camaraderie. If everybody's saying something negative about the person on TV, if you want to feel like part of that group, you got to sling out a few venomous comments yourself. And likewise, if everybody's like celebrating rapturous applause for someone on television, you're going to be like, oh yeah, I like that person too, because that makes you feel like a member of your social group. And you also feel like, well, if you have a dissenting view, it's very unlikely to have any impact because you have this perception that everyone around you has the same opinion. And there's a cost that you could be thrown out of your social group for having certain kinds of opinions. Political entities know very well that early opinions articulated about them will change whether or not they experience a positive feedback loop of popular opinions or positive feedback loop of negative opinions. And so a lot of strategy, a lot of money, 9-digit figures are spent on many, many elections to try to instigate these positive and negative feedback loops. And even if they're both happening at the same time, trying to sculpt the attention of society towards one of these things rather than the other, to try to bias this psychological predisposition for you to have similar opinions if you think it's the majority opinion. It's a tipping point, which is what we'll get to later on. And this causes stable social states where if you feel like almost everybody in the society feels one way, even if you can only detect one portion of the society, then you're going to continue to exhibit that opinion because dissenting opinions could imperil you. And if everyone in society has a negative opinion about something and you think that that's everyone in society, if you have a positive opinion, you want to be quiet about it, right? So politicians, Boris Johnson, conservative, Angela Merkel, from a very, actually amazingly socially progressive for having come from Bavaria. I think she's Bavarian. And I think although Bavarians are like famously quite pleasant and like, you know, effervescent, they're also like the dawn of a lot of really conservative political social views. Connectedness. All right, it's been 35 minutes. I should shut my trap. I'm going to go through connectedness and tipping points and hysteresis and early warning signs on Monday. So that should leave just self-organization, hierarchical organization, determinism and chaos, and the last third. So collectiveness is relatively short. I hope you're enjoying this. I hope it's making sense. I hope my cat examples and population examples, etc., are describing the general patterns of these systems rather than positive feedback loops and their importance. Don't get hung up on the particulars of any one system unless you find that it's easiest for you to think about all of these topics with one focal system in mind. Some nice student was like, I think you're overusing the word highfalutin in your lectures. But I use words so liberally, and I like to paint pictures with words in a really florid way. And so highfalutin basically just means floofy, fancy, like pompous, like frilly. And normally it's meant to be something like it's a pejorative, right? So like it's a degrading thing to say about someone, like, oh, you're highfalutin. Normally it's like somebody who is saying something negative about some overly fancy, frilly person, right? But I usually use highfalutin in more of an oblique way, like whenever something's super fancy in terms of like what it's capable of or the kinds of mechanisms that it's using. If they're sophisticated, if they're beyond the most basic levels, I will sometimes sort of like poke fun at them by saying highfalutin. I'm also from the South, so and we use the word highfalutin more regularly than other folk and such. Okay, I'm going to let it end there, but hopefully you're having a good time. I'm having a good time in this lecture, and I'll see you guys hopefully in office hours tomorrow. Have a good one. Take it easy. Bye.